So, picking up where we left off yesterday, let's see if we can apply the idea that we can find the average of a function on a closed interval. So on the closed interval from 0 to 3, what is the average for the function 4 minus x squared? This is me pausing, hoping that maybe then you'll say, you know, Mr. Pinner, this is really easy. This is what you do. We use that equation again. That my old book, instead of saying average of the function f, they use this notation. Well, actually, I always thought I looked at it, this is my favorite formula. This formula is my favorite. All right. So here's our formula again. Okay, let's plug and chug. 1 over 3 minus 0 on the interval from 0 to 3. 4 minus x squared dx. Right? Now, I'll clean this up and just change it to a 1/3. But let's talk about this part right here for a second. We don't have, right now, a good way of finding the exact answer, but we do have the ability to use our calculator to find it. So I would like to do this one graphically, if you don't mind. I'm going to go to y1 and put in 4 minus x squared. Everyone good?
Yep.
Let's do a zoomed standard. You know, let me zoom in on just the area that I'm interested in. From 0 to 3. How about from -2 to about 5? So there's my function. Let's find the area under the curve for this function. Second, calc, option 7. My lower limit is 0. My upper limit is 3. Okay. What's going on over here? This is going to be the negative area top. Okay, and so it's going to bring our average down, right? But we end up getting an area of 3 underneath the curve. So if that's the case, this is 1/3 times 3, or we're going to say the average of that function on that closed interval is equal to 1. It is very nice. All right. Hey, there's a second part to this slide. Does the function actually take on that value on that interval? Is there a place where the function actually is 1 on that interval? Can we find out at what value x that happens? When does 4 minus x squared equal 1? Plus, oh, okay, if I take this, I'm going to take the x squared over here. I'll take that, the 1 over there. I'll take the square root of both sides. And I get plus or minus the square root of 3.
But it's not defined.
But the negative root of 3 is not in this interval, but the positive square root of 3 is in this interval. Positive square root of 3 is like 2.6 something. Sorry, 1.6 something. 1.7 something. All right. So there is indeed a place in this interval where the function is equal to the average. Excuse me. I feel a theorem coming on. The mean value theorem for integrals. This is the second time that we've encountered something called mean value theorem. The first time was, we said, if a function is differentiable on a closed interval, somewhere the instantaneous slope is equal to the average slope. The mean value theorem for integration basically says if a function is continuous on the closed interval from a to b, somewhere on that interval, the average value of the function and the function itself have the same value. Or there exists a c such that f of c is equal to the average of the function. Do we? Definite? Yeah. It's definitely wrong. Would someone remind me, there's actually that error, there's one of the other errors that you guys caught yesterday I need to correct still. Someone remind me when I shut down, after we get done with the lecture, for me to correct those. So next year I won't be embarrassed by my poor spelling. Everyone okay with the mean value theorem? Now again, we just found that value c in the previous example. The value c was square root of 3, because the function at square root of 3 was equal to 1. The average value of the function on that interval was equal to 1. And this is true whenever f is continuous. Yes?
Is there a reason why there's no dx like that?
That would be a typo as well. There's actually 1, 2, 3, 4 errors on this page.
Why is C in there?
This is supposed to be like.
Because they're supposed to be they're supposed to be italic.
It's supposed to be what? Those are italic.
These whenever there's a letter that's representative of a number, it should be in italic.
Wait, okay, I have a question, but
Yeah.
this is kind of nitpicky. But so you said some point C, wouldn't it be C or f of C? Because that's a point. Like,
There exists some point c that's, remember this interval. These are
oh,
x.
that's
These
just
are x
x's.
values.
Oh, okay.
So c is in the right range,
Okay.
and then f of c is the right height. And just a reminder, can we compare and contrast this to the mean value theorem for derivatives? C exists such that f prime of c is equal to f of b minus f of a over b minus a. You remember that from a previous slide?
Yeah.
Okay.
It's just the opposite.
Okay. The criteria, by the way, f has to be if f is differentiable in the mean value theorem for derivatives, if f is continuous for the ones for integrals. Everyone okay with that page? Because now we're going to get to the meat. Now we're going to get to the good stuff. Assuming you're not vegetarian. Are you ready? Here we go. Did I assign through 17 already? Okay.
Yeah, but
That's all right. No, don't worry. I broke it up into 2 pieces for the other class, so, all right.
I stopped at 11 because I didn't know what to do.
Now you know what to do. Okay. Here's a journey that I need to take you on. This is the biggest thing that we're going to do all year, is this little piece of this lecture. All right? But I have to have you come along for a thought process to make it all work. I've got a graph there. Let's call it a velocity graph. I suppose you could call it Dave too, but I'm going to call it a velocity graph. Okay? So, let's say the horizontal axis are measurements of time in seconds. And let's say the vertical axis is measurements of velocity in feet per second. Everyone okay with that idea? Great. I want to introduce this new kind of definite integral. And in this case, it goes from 0 to x. The boundary, the lower bound is 0, and the upper bound is x. Now, since the upper bound is variable, that means you have to give me a value for x for this statement to be of interest. Let's say Charlie says, I declare the value of x to be 0. Then what's the value of that integral? 0, because it's going the integral from 0 to 0. All right? Chris, being unhappy with 0, because he thought it was sort of a lame thing to throw out there. Charlie, no offense. But he says, how about at 1? When x is 1, what's the value of that integral? 1/3, because we've done this problem to death. I say, Chris, what does that 1/3 represent? Well, it says the displacement at time x. But what does that mean? How far I moved. If I'm moving with the velocity as shown by that curve, that 1/3 represents how far I traveled when x was 1. In that 1 second, I traveled 1/3 of a foot. Using FNINT on your calculator, can you calculate what this would be at time 2? Can you calculate at time 2 how much I've moved? Eight-thirds says, Trevor, are you assuming that the thing on the thing would then convert to a nice fraction?
Actually, it does.
Well, maybe.
It does? Okay, great. So, if Chris says, so not Chris, you didn't say 2, you said 1. Who said 2? Nicole, you said 2, right? Okay, so Nicole says 2, and then we do some work, and we say 8/3. All right? Candace, you say 3, and then everyone says, oh, I can calculate how far this object has traveled over those 3 seconds. Do it for me really quickly. 9? Wait. Now we get into the point. Charlie says a number, Chris says a number, Nicole says a number, Candace says a number, and every time we do some work and we give a number back. What kind of relationship is that? You give a number, we do some work, and we give a number back. What's the relationship? It's a function relationship. Oh, wait. This thing here is a function. It's a function of x. More than that, it's a function of x that's returning something like a position. This integral returns something that's kind of like got a position. If I started at 0, when you said 1, it meant I moved 1/3. If I started at position 0, I've moved from 0 to 1/3. I'm at 1/3. It returned the position. When you plugged in 2, it returned what, 8/3?
Yeah.
It returned 8/3. It's like I'm at position 8/3. It's returning something that's kind of acting like a position. Are you okay with that idea? It's a function, and it's a position function to boot. All right. What would be the unit for this displacement? Feet. A linear measurement. What would be the derivative of this displacement? Velocity. Well, if we talk about it being not displacement, if I kind of cheat just a little bit and change the word displacement to position, are you okay with that? If I change this to position, indeed, the derivative of position is velocity. This is a very crucial step here. The derivative of position is velocity. The velocity at time x. This was our position function. And what I'm saying is, what happens if we take the derivative of this function we get back out by Jordan's knowledge of physics? We get back out velocity. Now this is really, really interesting. I've got a derivative here. I've got the velocity function there, and I've got the velocity function there. It seems like this integral action and this derivative action undo each other. I'm doing something to velocity, and it looks like the derivative undoes it because I go back to velocity. The integral does something, and the derivative seems to undo it. Yes? Go ahead, Edwin. It's anti-differentiation. The action of the integral is anti-differentiation. Because then when we take the derivative of it, it's like matter and antimatter, except without all the energy release. Well, no black holes here. The action of the integral is one of anti-differentiation. Because when I take the derivative of it, I go back to where I started. So, here it is summarized in a little bit more, I don't know, to simplify. All right. So let's start with this idea, and I'll finish off hopefully the big idea. Ready? We know this statement is true. It's where we ended up on the last slide. The derivative of the definite integral of the velocity function, and that's from a to x, is equal to the velocity at time x. Now what I'd like to do is I'm going to play with this symbolically just a little bit. And because not every time we ever do an integral is having to do with velocity, I would like to do this just using our standard function notation, not necessarily velocity. So let's say that these two things, with the exception of, again, changing velocity to f because it's more standard, those two things are totally equivalent, right? Right? If v and f are the same function. So f is just our generic function name. So that's going to be our starting point. The derivative of the definite integral from a to x of f of t dt is equal to f of x. Because of, again, that position-velocity relationship that Jordan talked about. Now, what I want to do is I want to take the antiderivative of both sides of that equation. You okay with that? It seems like a strange step, but I want you to think about taking the antiderivative of that. The antiderivative of a derivative.
So getting rid of well, essentially you're reversing the reversing.
Right. So when I take the antiderivative of this, the derivative part is going to go away.
And then you get it on
And I'm going to get an antiderivative on the other side. If I take the antiderivative of both sides, I end up getting just the integral left over on one side. This is the derivative part's going to go away, and I'm just left with the integral. And on the other side, I'm going to get whatever the antiderivative of f of x is. Now, we have a standard notation in calculus. The antiderivative, say an antiderivative of little f, has the symbol big F. The antiderivative of the function little g is given the symbol big G. So instead of calling it the generic, an antiderivative of f of x, I'm going to replace it with this notation. Big F plus the constant c. Remember c, right? It's the thing that makes an antiderivative into the most general antiderivative, something that represents all of the antiderivatives. So big F is going to be my idea of an antiderivative of little f, plus some constant c. And here's what I have. This integral is equal to this antiderivative plus c. Now, how can I find the value of c? Do you remember when we first did these problems? Is that Nicole? I got to know some point of the function. And this is where Charlie's stuff comes in really handy. Do you remember, Charlie, when we started with just this and we were trying different values of x? Do you remember the value that you gave out?
0.
Well, this was back when this was just a plain old 0. But now let's take it this way. Hey, how about, what would be the equivalent? Instead of starting at 0, we're now starting at the generic value a. What would be the similar thing to what Charlie did? How about we said, what is the value of this antiderivative, this integral at a, from a to a?
0.
Because we did that yesterday, didn't we? So this function, when x is a, is 0. The value of the integral from a to a of f of x is equal to 0, just like Candace said. And if I take that information, I get this. The integral from a to a of f of x, f of t dt, is equal to the antiderivative's value at a plus c. And this integral also has to equal to 0. When x is a, every place I see an x, I replace it with a, and we happen to know that that particular integral's value must be 0. Now, focus only on this part. Do I have enough information to find out what c is? Can I solve for c is another way of saying this. I can. When I solve for c, I get that c has to be negative f of a. When I take the stuff that's in that last blue box, solve it for c, I come to the conclusion that C must be negative f of a, negative big F of a. So here comes the big finish. Ready? Our conclusion then is that the integral from a to x of f of t dt is equal to big F of x minus big F of a. The integral from a to x of f of t dt is equal to big F of x minus big F of a, where big F is the antiderivative of little f. That's a very circuitous journey to come to this really, really great conclusion. Let me see if I can summarize. Okay, the journey is important. The conclusion is what you have to really leave here with. I need a blank slide to conclude this. That means if I give you a problem like what is the integral from 0 to 1 of x squared dx? Thank you. No? Okay. Not today. Maybe over the week. You got 3 chances over the weekend. So, all right. I could say this is going to equal to f of 1 minus f of 0, as long as f is an antiderivative of x squared. What is the antiderivative of x? What function could I write here that if I took its derivative, I get x squared? 1/3 x cubed. Let me try that. If I took the derivative of this, the 3 comes down, changes into a 1, reduce the power, I get x squared. This is the antiderivative of that. So this integral is equal to f of 1 minus f of 0. Wait a second. What if this was the integral from 0 to 2 of x squared dx? It would be equal to big F of 2, big F of 2 minus big F of 0. Well, what is big F of 2? 1/3 times 2 cubed minus 1/3 times 0 cubed. 2 cubed, that's 8. 8 over 3 minus 0 is 8/3. That number sounds familiar. And what would happen if I did this problem one more time? It's big F of 3, can't write that low, minus big F of 0, 1/3 3 cubed times 3 cubed minus 1/3 times 0 cubed. 3 cubed is 27. 27 divided by 3 is 9. 9 minus 0 is 9. Now, these are not approximations. These are the answers. Those really are the areas under that curve on those closed intervals. Finite integral gave us really great estimations that these are the answers. Yes?
Could we do this with a trigonometric function?
How about the trigonometric function sine of x? Okay. What I want you to recognize is that we can find the value of that definite integral by saying, oh, it's going to be big F at pi minus big F at 0. And now what I need to know is, what's big F? Cosine of x. Because when I take the derivative of cosine x, I get negative of negative cosine of x. Because when I take the derivative of negative cosine of x, I get negative. Here, let me just write that up. F prime, negative, and then cosine is negative sine. Those two cancel, and I get sine. Okay, so I agree that that's the antiderivative. So what is this going to equal then? This is going to equal to the value of negative cosine at pi minus negative cosine at 0. So this indeed becomes a plus. Candace, you're absolutely right. What is cosine of pi? Cosine of pi is negative 1. So this is the opposite of negative 1 plus, what is the cosine of 0? 1. Can you use the finite integral function on your calculator? Or go into the graphing mode? Wait, did we do this in graphing mode a couple days ago?
Yeah.
Can you just let's just confirm that. If you look at that graph, and then you will confirm that that's what the estimation gives you as well. No, that's good. You just go to second calc. Oh yeah, you had to convince it to redraw it. Okay. And that's an extremely powerful idea, that the integral, which we said represents area under the curve, can be found by using antiderivatives. Extremely, extremely powerful idea. Who came up with that? Newton and Leibniz.
But did Newton actually come up with the integral too?
He used a different notation. We are using Leibniz notation because Leibniz published where Newton did not. Here's what Newton did. Newton, in his crazy ways, says, you know what? I don't see any data that contradicts Kepler's laws of planetary motion. The story goes that Kepler saw that the planets must be moving around the sun. He had these extremely, really accurate measurements of the movements of those planets. And he said, I think they move in circles around the sun. But the measurements were inconsistent with that. After years and years, Kepler says, here's what I really think is going on. And this is what fits the data. That planets move around the sun where the sun is at one of the focus of an ellipse. That's law number 1. Law number 2, that the speed of those planets change such that the area swept between the sun and the planet is equal for equal times. And what's the third law? It has to do with the distance from the sun. I thought it was the second law. Okay, if it comes down to that, Kepler says, here's what I got, and here's what matches the data. But Kepler doesn't know why. Newton says, I want to show why this is true, not that it is true based on the data. Newton creates calculus, which he called fluxions, as a tool set to attack Kepler's problem. But he didn't share it. He didn't publish it. He didn't tell anyone that he did all this fundamental work with mathematics. All he says, I know that Kepler's right.
Oh, it's I know what the third law is. It's like something having to do with the period of the planet.
Okay,
It's like
how quickly?
cubed equals
It's like there's an inverse relationship between the distance and the period that the planet takes to get around it. Yeah. So anyway, so Newton does all this work. He comes to all these conclusions. He finds the relationship between the what we're calling the integral and the antiderivative, but he never tells anyone. And then 30 years later, Leibniz does the same work using a different notation, but the same general ideas. But he publishes. He calls it the calculus.
Doesn't he steal it from?
No, Leibniz never stole it. Well, at least the historical record doesn't suggest that there was a steal. There were sometimes two ideas happened at the same time. Newton was first. Leibniz was first to publish. And that's why we use the Leibniz notation for integrals and for derivatives. But it wouldn't it be more fun to say fluxions?
Yeah, it is a sweeter. But Mr.
Yes.
I thought Leibniz did more work on the integral end, and
You did more on the differential end. Yeah, but it's still Newton did know this relationship of the integral and the.
So he did.
Right, because otherwise you can't do the area sweeps, because that's an integral. It's an area. All right. So here's what's true now. Given this newfound power, the relationship of the definite integral and the antiderivative, you can do the rest of the problems in the problem set. All right? Schedule is on Monday, we'll do questions, and on Tuesday, we're going to quiz 5.1 through 5.3. Also next week, on Wednesday afternoon, after school, I'm going to do the second marking period makeup exam. If there are any exams that you would like to replace from the second marking period, which essentially would be either test 3 or test 4, you could take the makeup test on Wednesday afternoon. If you want to replace those exams, if you're a Berkeley student, I also offer that same test on Thursday morning at 6:30 with me at Berkeley High. Trevor.
Can we look at our test scores?
Yes.
Decide.
How about on Monday? I print out a grade sheet for you, and you know where you stand.
Yeah.
Great.
Will we all get that grade?
Yeah, everyone will get a grade sheet.
So is it was the last grade?
Yeah, quiz will be the last grade. All right.
Oh yeah.